Alright, so the first thing we're going to do is open a data table so we can try out some of the regression functions. Now the data table we're going to use is from Kennel, the 5th edition, and it's the Chapter 1, Problem 19 file. Now if you haven't opened this before, we're going to have to go through a little bit of work to get it to open in the correct format. You'll notice that I have in this folder a version that's already been saved as a .jmp. But let's actually go through opening it from the text version. So once you have it selected, if you're on a Mac, you're going to select Data using Preview. If you're on a PC, you'll also select this, but it'll be in a slightly different section. Go ahead and hit Open. Now notice that by default, delimited fields is what is selected, but we don't want to actually use that. The way these data are stored are using fixed width fields. So go ahead and select fixed width fields, and what this will do, as you see, is separate the two different fields we have, basically finding that the things that line up on one side fit into one column, and these all fit into another. Go ahead and hit Next. If we want to, we can label these column headings right now. If we double click, we can call this GPA, and the second column is ACT. These labels you could find by reading the chapter for where the data set was introduced. Notice that ACT scores are over here, except that the way this scaling has worked, they've gone to the side. So now we have everything set up. Go ahead and click Import, and you'll see that our data now is all in the format that we need it to be. Now the first thing we might want to do once we have our data open is look at the individual distributions of each of these variables. Now, this is a good habit to get into, both so you get familiar with what your data look like, but also to make sure there aren't any extreme values or things that shouldn't be there that you can fix right offhand. So go ahead and go to your Analyze menu and go to Distribution. And what I want you to do is take both of these variables and just put them into the Y columns here. And what this is going to do is for each variable produce a separate plot of the particular distribution of that variable. So go ahead and hit OK. And you'll see for each of our variables we get the plot of what values have occurred within that column. If your plots right now are in the opposite direction, that is they're plotted as columns, you can go up and select Stack under this little drop-down triangle. And what that'll do is convert them to the way that I have mine set up. Now from a first glance, there doesn't seem to be anything particularly strange here. If we had, for example, a GPA that was at 7 or something like that, we'd be able to catch it. You might notice that it seems as though we have a GPA that's between 4 and 4.5, but this probably isn't the case. It's in fact just a scaling issue. If we drag this out a little bit, and in fact if we select the hand, we can rescale these into different bins. We can probably see that that's probably an exact 4.0. And indeed, if we look at the quantiles, the maximum score is in fact a 4.0. In the same way, if we look at the ACT scores, we can see our maximum is 35 and the minimum is 14, and these fall into the ranges we should expect for these particular columns. So let's go ahead and close that distribution plot. Everything looked okay there. Now what we're going to do is launch the Fit Y by X platform, and this is one of the two ways that we can actually fit a regression model to these data to see what predictive power one variable has for the other. So go ahead and start Fit Y by X. And before I go any further, I want you to notice that this platform is very flexible. It'll take data types that are nominal, ordinal, or continuous and compute the correct relationship or correct fit between the two. So for example, if you have a continuous variable and you're trying to predict, in this case, an ordinal or a nominal, this platform will know to perform the logistic regression for you. In our case, we have continuous by continuous, and what that is going to do when we put those variables into this platform is produce a bivariate fit for us. That is, it'll give us the option of fitting a line or second or third or up to 6th order polynomials, as we'll see. So for now, let's put GPA as the thing we are trying to predict, so as the Y, and let's put ACT as the factor, that is the thing that we're trying to make predictions from. And of course, it's a little bit arbitrary which one of these we put into each section. Of course, we can talk about predicting ACT scores from GPA, but the way the book lays it out and the homework questions, typically GPA is the thing we are trying to predict. It is the criterion. So once you have those set up, go ahead and hit OK. And what you'll see right off is just the scatter plot of these data. That is, for every individual person, you'll get the plot of their ACT and GPA. So each dot in this particular graph is representing a single individual. And you'll notice what I was able to do there. If I drag a selection around any person, I can actually find them in the data set. And this is a real flexible use of JMP and a nice way to be able to find people who fall into different categories. Now you'll notice we don't actually have any fit here. We haven't fit any particular line. To do that, we have to go to the drop-down and go to Fit Line. And what this is going to do is perform the least squares regression for us. It's going to fit a line that minimizes the sum of the squared distances from each individual point to the value that the line would predict for that individual ACT score. That is, for the variable on the x-axis. And you'll notice that it fits this line, and if we line this up with what we would have predicted the best fitting line to be, it should probably fit with our intuition. If you look at this, it seems as though there's probably no other line that would fit better. And in fact, that's what the least squares linear solution is. It is, in fact, the line that fits the data best by the criterion of the sum of the distances from the points to the line being a minimum. Alright, so let's step through what output we have here. The first thing you'll see right here is the actual fit solution for this line. That is, it's saying the prediction of a GPA score, that is the y hat, for any particular xi, is equal to the intercept 2.114 plus, here's the slope estimate, 0.0388271, times ACT. So what you can read this as is the intercept of this function is predicted to be 2. That is, if somebody had a 0 ACT score, the best guess this line can make for us is that their GPA would be a 2.0. Now you can wonder if that's actually a reasonable thing for the line to predict, but of course it has to place the intercept somewhere. Now the slope parameter here tells us something different. It says for every unit of ACT score increased, how much of a GPA increase should we expect on average? And in fact what this says is that for every ACT score increase of 1 point, we expect an individual's GPA to be 0.038 higher. And if you look at the line here, this is exactly what it's representing. For every 1 unit increase, the GPA predicted for people is going to be 0.038 units higher. Now under summary of fit, we have a couple interesting statistics that are reported for us. The R-square may be a value you're familiar with. This is the percent of variance accounted for in the predicted variable from the predicting variable. That is, 7%, or 0.07, of GPA is predictable from someone's ACT score. Now this isn't a very high value. If you think about what this means, it's that 93% of the variance, that is, of the differences among people in GPA, are unpredicted or unaccounted for by ACT scores. So ACT scores are not a particularly good predictor of GPA by this metric. The R-squared adjusted is a slightly different calculation of R-squared that takes into account the number of parameters. And the reason why you might use an R-squared adjusted is if you have a model with a huge number of parameters and you don't want to have your R-square be inflated by the mere fact that you have a huge number of parameters to predict whatever your criterion is. The root mean squared error is exactly what it sounds like. It's the square root of the mean squared error of the model. That is, this is your estimate of the population standard deviation. The mean response, this is your average y-score. So this is the average GPA you observed in your data set, irrespective of ACT scores. This is just the mean of the y's. And finally, number of observations you had. We had 120 individuals in this particular data set. Now of interest may be this analysis of variance table, because this is going to report out for us all the different values that we've come to know from actually studying what a regression analysis is. Perhaps the first place you might want to look is the probability greater than f and the f ratio. Now what this is the overall test of model fit. That is, do we have evidence, based on the sample that we have here, that there is some relationship between ACT scores and GPA in a population? Of course, the slope for any particular sample will probably be non-zero. What we want to know is if the model overall is fitting the data better than it would by chance? That is, do we have evidence that somehow this model is different from just one in which we have no predictive power? And that's what this omnibus, or this overall analysis of variance test, is going to tell us. Does the model fit better than pure chance might alone? And it does. Our p-value is very small here, 0.0029, and if we were testing at an alpha equals 0.05, this would indicate to us that there is actually predictive power here. Now, perhaps even more important to us would be the tests of whether the intercept is different from 0 and whether the ACT parameter, that is beta 1, our slope parameter, is different from 0. And those two tests are found under the parameter estimates section. Now first, this intercept term, you see we have an estimate of it here, 2.11, and this corresponds to, of course, our intercept up here of 2.11. It tells us the standard error of the intercept, the t ratio, and the probability greater than the absolute value of t. Now what this is telling you essentially is the two-tailed p-value. So, based on our sample and the estimate of the intercept we've received, what we see here is that the probability is very low that we would have received such an extreme or large intercept if in the population it really was equal to 0. That is, we can reject the null hypothesis that the intercept is equal to 0. And this seems pretty reasonable considering that, given these data, our intercept is pretty far up. Right? We wouldn't expect, if the population intercept really was 0, for our estimate to be 2.11. And that's exactly what that p-value is reporting for us. Now, probably most interesting to us is our estimate of the slope parameter, our beta 1 in this particular situation. And for us, we're modeling, of course, ACT, so the question is really, does ACT have some predictive power for GPA? Is there some relationship between ACT and GPA in the population? Now, our estimate might look small, 0.0388, but notice the standard error of that estimate is also incredibly small, giving us a t ratio of 3.04 and an associated p-value for two tails of 0.0029. Now what this of course indicates to us is that we have evidence that the population relationship is non-zero. That is, that the slope of this line in the population is not 0. Basically what this p-value is reporting for us, like all p-values do, is what the probability is that we would receive an estimate this extreme or more in either direction if in fact the population slope were 0. And what we find here is that it's unlikely, and more unlikely than our criterion, which is probably alpha equals 0.05, it's more unlikely than that, so we're going to reject the null hypothesis. That is, saying that there is no relationship in the population is not a very good summary of what's happening here. That is, we rejected in favor of the alternative hypothesis that truly in the population there is some relationship between an individual's ACT score and GPA. Now notice, we're not making any causal claims by doing this analysis, and in fact our statistics are completely agnostic as to whether there's a causal relationship here. All that we can say is that there is some statistical relationship. There is some predictive ability given to us from ACT scores to find someone's GPA. And this probably makes sense if we think about it a little bit, that probably what's in common with these things is someone's intelligence, motivation, perhaps how much they study in school. There's many factors about a person that it would make sense would lead to somebody who has a high ACT score to also have a high GPA score. So we don't need to make a causal argument, we just simply need to make an argument that there's some association here. Now that we have our output, there's a couple of extra things we can do with this particular fit. Now the first thing, and this is something you may want to do in any output when you're looking for a specific value, is just simply right-clicking on each of these sections. So if I right-click, I'm not sure why that went up there, but notice that under columns of the context menu that pops up, I can request the lower and upper 95% confidence interval on my parameter estimates. So if I select these, you'll notice now I have actually the lower and upper 95% confidence intervals for my intercept estimate and for my estimate of ACT scores. Now these are very useful, of course, if you would like confidence intervals rather than simply the hypothesis test, to give you an idea of where these parameters probably are in the population. That is, our best guess of where the true parameter is somewhere between 1.47 and 2.74 for the intercept, and between 0.01 and 0.06 for the parameter estimate of ACT score, or for the slope parameter. Now under analysis of variance table, if we go to columns, notice that everything is already lit up for us. That is, by default, the analysis of variance table will print out everything. And notice that we already have our model sums of squares. So these are the sums of squares that the model accounts for, and the associated mean square. And we have our sums of squares for error and the associated mean squared error. And of course, these are the two values that then go into computing the F ratio for us. But notice there's really no other values we should expect to be able to get within this section. Under summary of fit, if we go to columns, there's already everything selected. And lack of fit, a section we haven't talked about yet in class, but notice that all the sections are already revealed for us. So under parameter estimates, that's the section in which we would have to actually request something extra if we wanted the lower and upper 95% confidence intervals. Now additionally, if we go to the drop-down menu here, you'll notice that we have the option of fitting different types of relationships beyond just a linear fit. That is, we can fit a polynomial, we can fit splines, we can fit orthogonals. We have many different options here. Of course, for this particular section, we're simply doing simple linear regression, so we're not going to do anything else there. Now finally, under the linear fit dropdown, so not the overall context, but specifically the dropdown for our particular fit, there's a number of things in addition to just the model fit and report that we can request. First, we can actually request a confidence interval or confidence curves around our line. So if you select these, notice that what it's going to do is actually give us a confidence interval around the line for where we expect the mean response to be. And that would be the confidence curves fit. Now the confidence curves for the individual, now these are the actual confidence limits if we're trying to predict an individual score. So this is the distinction between trying to form a confidence interval for the mean response versus a confidence interval for an individual that we might be taking a sample from with that particular ACT score. So, of course, this is the difference of if somebody has a score of 25 on the ACT and we want to know what that actual person might have as a GPA, that would be the confidence interval for an individual. If instead we're trying to say for all people who have ACT scores of 25, what is their GPA? That's this confidence interval for just the mean response, or that first one, the confidence curves for a fit. Now, already it's fit for us, these lines. It didn't ask us for an alpha value, and the reason why is because this is already set under here as a default of 0.05. If you would like to set a different alpha level for these particular confidence curves, you can. So we can go in and set 0.1, and notice that at a 90% confidence, or an alpha of 0.1, these lines are a little bit closer in. And this should make sense for you, because what this would mean is that a lower t value is going into the calculation of these confidence intervals. That is, at alpha of 0.1, we have a smaller value of tconf than we would at alpha of 0.05 or alpha of 0.01. If you prefer these fits to be shaded, you can actually request that here, confidence shaded fit, and it gives you a nice little coloring of that line. You can do the same thing for the individual if you would like, and it will give you the nice little shading in there. Now, one thing that will be useful for us later on is the ability to save predicted values and residuals. So remember, predicted values are for every ACT score in our data set, the values it would predict for someone's GPA. So if you go ahead and click that, you'll notice what you're going to get, we scoot this aside, is a new column in your data set that shows the predicted values of GPA for every person in your set. So for this person who had a value of 21, their predicted GPA is 2.92. And notice that all JMP has done here is take the actual model equation it's come up with, our best fitting linear least squares equation, and it's simply putting in 21 where it sees ACT, and it's calculating this out for us. Now if we go back to this drop down, you'll see the other thing we might be using later on is saving residuals. Now remember what the residuals are. These are the actual observed E sub i's. That is, for every individual in our data set, there's actually a difference between their predicted GPA and the GPA the data set actually had. So in this case, the predicted GPA of 2.9 for this individual and their actual GPA of 3.897, gives us a residual of 0.96. That is, the model was off by 0.9675 for this particular individual. And so every individual is going to have a different residual. And you can see, if we select any one person where they are in this plot, you can see if we find somebody with a very large residual, it makes sense that they're the person who's really far from the line. This is a person for whom the line was a very poor fit. And there's a couple things with the residuals that we're going to end up using later, specifically for doing diagnostics on whether our regression is actually appropriate for the particular data. And one thing you'll see we do quite often is actually plotting the residuals. So if we go to Analyze Distribution and actually give the residuals as the thing we want to plot, you'll see that we can get an idea of what types of residuals we had, or instead other ways, how the model was erring. Was it erring in a pretty normal fashion? That is the distribution of the residuals fairly normal? Or was it erring in a very strange way, like a skewed pattern? Did we tend to have lots of extreme negative errors, but not a lot of positive errors? And diagnosing the shape of these residuals is going to be important for specifically our model assumption of normal error terms. That is, we assume with regression, at least the standard linear regression, that our error terms or our errors are normally distributed. And we are going to be able to do diagnostics looking at whether we really have reason to believe that that is the case. So returning to our fit here, you'll see that we were able to perform a great deal of analysis and get a great deal of information simply from this fit Y by X platform. That is, we were able to get all the information about our model fit. We were able to fit confidence intervals for individuals and for the mean response. And we were able to save the predicted values and our residuals. But notice that's about all we can do. We really can't do anything more complicated with this particular platform. And in fact, there's another, probably more flexible way that we're going to end up handling fitting regression models as we move forward in the class. And that's to use this Analyze Fit Model platform. Now, the Fit Model platform is a little more flexible because it gives us the ability to have not just a single predictor of our y-score, but multiple predictors. So as we move forward in the class to multiple regression, we're going to have to use this Fit Model platform in order to actually produce our estimates and to fit the regression parameters that we end up using. So let's look at how we would actually do this for our simple regression case. Now notice that we're not going to get any different values here. It's just going to be that the model will be fit using a platform that gives us some different options. So again, let's take GPA and put that in the Y, and let's take ACT and put that in our model effects. And notice that to get there, I simply clicked on ACT and clicked Add. I could have also dragged ACT down here, and it would actually put it into this model effects section. And we don't have to change anything else at this point. We can simply click Run Model. But before I do, I want to make a note about this personality and emphasis section. Now, if you click on personality, you'll notice you have a number of different options. Now, this is really the type of model that you are asking JMP to fit for you. For most of the class, we're simply going to use the standard least squares. That is, this is the standard model fit that tries to minimize the sum of the square distances from the model to the line. From the model to the data. But notice we have other options. We can do stepwise regressions, multivariate analysis of variance, or log linear variance models. If we were trying to predict a nominal or ordinal outcome, we would have the option of nominal and ordinal logistics. And we also have proportional hazards and parametric survival tests that we can do. And then finally, the most general of all these is the generalized linear model, which would let us specify a link function and let us fit models that are within the general linear family, but apply to different sort of outcome situations. But for now, let's stick with standard least squares. That's all we have to do. Under emphasis, this is actually going to determine not the type of model we fit, but just the type of output we get. Effect leverage is a fine output type. It'll give us some things we don't need right now, but it's a fine thing to keep as just a default. If you want the minimal output, you can select minimal report, and know that after you actually fit the model, you can always request more things to be printed out. So emphasis here is really just an idea of what template you want it to use for your output. Do you want it to give you, by default, a number of things or just a few things? But effect leverage is fine for us at this point. So let's go ahead and click Run Model. And you'll notice that our output looks a little bit different than it did when we used fit y by x. First, we have this leverage plot, which we're not going to get into right now. So what I'm going to do actually is minimize this. I'm just going to click the little triangle next to it so we don't have to keep looking at it. I'm also going to minimize this actual by predicted plot because this is something we're not going to get into quite yet. So notice this regression plot. This is actually what we saw when we did the fit y by x. That is, this is our scatter plot of ACT and GPA with the line already fit to it. And this is the same linear least squares line that we found before. In fact, if it differed, we would have some trouble. Notice that we have the same summary of fit section here. We have the same R squared adjusted, the root mean squared error, mean of response, and the observation count. We have our same analysis of variance table, and we have the same lack of fit table, which we haven't talked about quite yet, so I'm actually going to minimize that. And we have our parameter estimate section, which everything looks to be the same as before. Now finally, we have this residual by predicted plot. Now this is going to be something important for us when we actually get into diagnostics. The idea is we don't want our residuals to have any relationship to the predicted values. That is, we don't want to be making errors of different types depending on what the value is we're predicting for an individual. This would be akin to saying we can predict really well for people around 2.0 GPA, but really poorly for people around 4, or some sort of relationship there. We don't want any of that. We basically want our errors to be evenly spaced across the entire range of predictions. That is, partially we want homoscedasticity, we want the variance to be equal, but we also don't want the skew of our residuals to be anything at all. We want our residuals simply to be random error around our prediction line. Now the reason why we might want to use the fit least squares or the fit model platform rather than fit y by x is because of the extra options we're going to get under this dropdown. Now notice they're even grouped, because there are so many, into separate sections. First, let's take a look at regression reports. We actually have everything already printed out for us. These are all the reports it can give us, or all the values it can give us for the different standard tests. Under estimates, we have a number of things that we can request. First, the prediction equation, if we request this, is simply going to show us the line prediction equation that we saw before. So let's go ahead and select that and scroll down a little bit, and you see we get the same prediction expression here, 2.11 and some change, plus 0.038 times ACT score. If we go back up to estimates, we can request sorted estimates, which is something that won't be really necessary until we actually have multiple predictors in our model. But what sorted estimates will do for us is actually show us which is the best predictor, and then the second best predictor, third best predictor, all the way down to the last predictor in our equation. So if we're trying to make selections based on a number of predictors for a particular outcome, sorted estimates is an actually nice way to look at these. Expanded estimates is something we might be interested in. What expanded estimates will do is actually just give us a little bit of extra information about our estimates if we have a model with lots of extra terms, especially when we have models with interaction terms. For our simple regression, notice that expanded estimates looks exactly the same as our parameter estimates section. That is, there's no extra parameters that it was hiding from us. But again, when we have models with interaction terms, often it won't be displaying the entire list of parameters because, of course, there's going to be some redundancy. Let's go back to our estimates section here. Sequential and custom tests we'll come back to later in the quarter. Inverse prediction is going to be something that is of use for us actually early on. Inverse prediction is sort of doing the opposite problem or the inverse problem of what we normally do with a least squares regression line. That is, normally if we fit the model with ACT as the predictor and GPA as the criterion, that means we're probably trying to make predictions from ACT to GPA. But imagine that we had a student come in and we know that that student had a 3.0 GPA and we want to predict what their ACT score is. That is, we're predicting in the opposite direction. Now, actually finding the predicted value will be pretty simple for most of us. We simply have to rearrange this formula. But the complicated part comes in when we're trying to fit a confidence interval, because we simply can't use the mean square error from our original model. We have to make adjustments, or we have to do something different. Because of course our model is trying to minimize the distances from the line to the GPA, not minimizing the line to the ACT. That is, it's a slightly different formulation of the problem. But lucky for us, with JMP, we can simply put in 3.0 here and say that we're trying to find a confidence interval with respect to an individual rather than the mean response, which is the same thing as saying we're trying to predict a confidence interval for a specific person who has a GPA of 3. And when we click Run, it's going to produce this confidence interval for us without much problem. It's going to say the predicted ACT score is 22 with a lower limit of -20 and an upper limit of 63. So this might be a particularly useless confidence interval for us, but it is in fact the correct one. Going back up to this section here, let's look again at estimates. We have parameter power and correlation of estimates. These things won't be fairly useful for us until we get to multiple regressions, so we'll stay away from those for now. Under effects screening, again, these are situations where we have more predictors, so we're actually not going to look at those. Under factor profiling, I'll show you what profiler looks like right now, because this is actually a pretty neat function. It gets to be especially interesting when you have multiple predictors, because it'll actually let you look at the prediction profile across the range of the model fit. But what prediction profiler lets you do is just drag along your line here, and it'll give you for any value the prediction plus or minus whatever amount. So this is giving us essentially, let me expand this out a little bit, the confidence interval for the mean response. So for individuals who score 30 on their ACT, the GPA we would predict on average should be 3.28 plus or minus about 1.7. So this is the prediction interval or the confidence interval on the expected response, or for the mean of all the people who score 30 on their ACT. But prediction profiler, again, will really be most valuable when we start having multiple predictors, because what this allows you to do is set in a value for each of your predictors, and it'll eventually, or it'll result in the output of whatever prediction you're trying to make for GPA or for whatever your criterion variable is. So prediction profiler is a very, very useful feature of this fit model. So we've covered factor profiling. Row diagnostics give us information that we're going to be using when we actually do diagnostics for our model fit. So things like leverage plots, residuals by predicted, residuals by row. But we'll cover that in a separate video. But finally, the save columns section. Now, we already saw two things we could save when we did fit y by x, but notice that we can save a whole lot more from this model fit. We can save the predicted values and residuals. We actually already did save these. We could also save the prediction formula. And as you know, JMP has the ability to set columns with formulas. What prediction formula will do is in fact create a new column that, instead of just having the values, actually saves the prediction equation. So what we can do now is actually enter in more rows of individuals' ACT scores, and this column, because it's computing these values on the fly, will actually give us estimates based on this prediction equation of those individuals' GPA scores. So this is a neat little function that it can do for us. Let's go back to save columns and look at some of these other sections. It'll also allow us to save mean confidence intervals and individual confidence intervals to our data set. So for example, if I select individual confidence interval, for every value in my data set, that is for every ACT score, so each person in my data set has an ACT score, it'll save for us the individual confidence interval on GPA. That is, the model's best prediction of where that individual's GPA actually would be in the population. So for a new individual who has a score of 21 on ACT, our best guess of what their true GPA is between 1.68 and 4.17. Now notice that's a fairly wide confidence interval, but this is the confidence interval for an individual. And of course, as we know, that encompasses both the variability to do with the prediction, the actual intercept and slope, and also the variability around the line. That is just the extant variability in the distribution of GPA scores, even if the line is perfectly fitting. So this lower 95 and upper 95 is really encompassing a whole lot of variability, so we should expect it to be pretty large. Now, if we wanted a different confidence level than 95%, the way you're going to set that in JMP is through a little trick of just holding down the Shift key before you click on this drop-down. So I'm holding on the Shift already. I'm going to go to Save Columns and again request the individual confidence interval. And notice now JMP is prompting me to enter my alpha level. So this time, let me specify an alpha point. Let me actually do 0.20. So this is an 80% confidence interval. And after I select that, notice that my 80% confidence interval is a little more reasonably scaled. That is, it's predicting for an individual with an ACT score of 21, a confidence interval between 2.11 and 3.73. So our best guess of where that person's true value is falls between those two values. And this idea of holding down Shift, or this trick, works in any section where you're trying to do something that needs an alpha value. JMP will typically default to 95%, but if you hold down Shift and select, for example, the mean confidence interval now, it'll again prompt you for an actual alpha value. So if I put in here again 0.20, it'll print out for me the confidence interval on the mean response now using an 80% confidence interval. And while we're on that, notice that the mean confidence interval, that is for the mean response of all individuals who have an ACT score of 21, is much less wide than our confidence interval for an individual who has a score of 21 on the ACT. And again, this is because this mean confidence interval is only taking into account the variability of our estimates of the intercept and the slope, and doesn't have to deal with the extra variability of the individuals around the line that just happens to exist there in the actual population. So going back to Save Columns, notice that we can save several other things, and these are going to be useful for us later in the class. The studentized residuals, this is a formula that basically converts our residuals into a standard form so that we can do tests on them to see if they are more extreme than we should expect them to be by chance. The hats, these are the diagonals on the hat matrix, or the leverage values. So this is something we'll be using later on, again, in our diagnostics. Standard errors of predicted and residual. These are the actual standard errors for these things, so for the predicted values, for the residuals, and for an individual. And so these are the actual values that go into making the confidence intervals and our studentized residuals. Effect leverage pairs and Cook's D influence, these are, again, things that deal with how extreme residuals are. So when a value is very, very far from what the line would predict, their Cook's D is going to be large and their leverage is going to be large. That is, they exert a huge amount of influence on the regression equation. So this is why when we have outliers in our data set, we want to find them early on and deal with them rather than have them unduly influence our regression equation. And finally, the standard error prediction formula and coding table. These are things we'll come back to later. But notice that under Save Columns, we really have a lot of options here, and a lot of options beyond which the fit y by x would have offered to us. So really, the best habit to get into now is whenever you're trying to fit a regression, instead of using fit y by x, just go ahead and start with fit model and get comfortable with this platform, since it's what we're going to be using most of the time when we actually are trying to do our own analyses.